This is Frame by Frame, Season 2, Episode 5. Today we'll be looking at optimizers.
I am Optimus.
That joke was a bit of a stretch, but anyway, let's review where we are in the neural network process. So up until now, we've discussed the entire process of sending data through the model as part of the forward propagation steps. We break apart the data into batches and feed images into the input layer, where those images will be broken down into the pixel values and they'll be sent through the model. We attach weights and biases at each node to send the output value through activation functions to introduce nonlinearity. And then we send along a single value after that into the next node. Maybe for some layers, we'll have some convolution layers, which will help lower the overall size of the image to help on computation. At the very end of the network, we'll apply a softmax function to the outputs, which will give us the probabilities that all sum up to 1. So each of these probabilities will correspond to a class in the data set. And finally, we will compute the loss function comparing our model's predicted value to the true value, because we want to see how far off our predictions were from the ground truth labels. The lower the number, the better our model is at predicting when compared to a real data set. So the next step in this whole process is to use the loss function value output, and we're going to see how much every single one of the weights has contributed to that output. And we're going to go backwards through the system and adjust every single weight so that we can have an even better prediction on the next pass. So our model here is going to go layer by layer, going backwards, trying to figure out the gradient of this loss function with respect to each of the weights. It's going to do this using the chain rule from calculus.
Look, so cute.
Remember that our goal here is to minimize the loss function so that our model can perform even better on unseen data. So we're going to be sending the error backwards through the system so that we can see how much each one of the weights has contributed to this loss function. This process of sending data backwards through the system after the forward pass is called backpropagation. So here's the general formula for updating the weights. All we have done so far is just calculated the gradient of the loss function with respect to each one of the weights. We're going to be taking that weight and we're going to update it using that new information that we just got. The only thing we need to do to get a new weight is to take the old weight from the forward pass, subtract it from a learning rate times the gradient of the weight at that spot. So this term here is just our loss function with respect to each one of the weights. This was calculated during our chain rule step. The technical math term for this is actually a partial derivative. So that's going to tell us how sensitive the loss function is if we were to tune any single weight at any time if we were to hold all the other weights constant. A neural network might have millions of nodes in it and millions of weights in it, but each weight is going to have its own partial derivative to tell how much that weight contributes to the loss function. This is really great so we can see how the loss function changes. If we were to shift one weight just in the positive direction or the negative direction just a little bit, how much the loss function would be changing. Looking at how each one of these weights changes the loss function value is the actual optimization of this process. The last term here is a learning rate, which is just a small value that we select to adjust the sizes of the steps taken to find the minimum of the loss function. It's usually a small value between 0.01 and 0.001. An analogy for the learning rate is like if you were on top of a hill and you're trying to hike down in a timely fashion. You're the optimizer trying to go down the hill, and this hill is like the gradient of the loss function. You're going to be taking smaller steps because you don't want to take too big of a step and hit a rock potentially, but you also don't want to take too small of steps and get to the bottom as a couple hours later perhaps. You want to find that perfect sweet spot so you can take equal amounts of steps and make it down the hill in a timely fashion. We're going to be doing the same thing with this learning rate, adjusting the size of it so we can get to the minimum of the loss function in a timely fashion. If our learning rate value were to be too big, we could overshoot this minimum value, and that wouldn't be good either. This method of updating the weights is usually just a vanilla version of gradient descent, and it's usually called stochastic gradient descent, where the learning rate is just the same value for the entire thing. That's like if we were trying to hike down that hill and we're going to be taking 2 footsteps lengths every single time down the entire way. Now, realistically, if you were trying to scale down a hill or mountain, you'd be adjusting the sizes of your steps as you go on. And we can do the same thing with our gradient descent by adding in a momentum term. Now, this is going to be called stochastic gradient descent with momentum. What the momentum does is it speeds up our training by accelerating our momentum in the right direction of the gradient by taking a fraction of the previous gradient when calculating the new one. Now, adding in this momentum term is a huge step up from the original stochastic gradient descent. It just adds in a little velocity term that keeps a running average of the past gradients so that it can use that as momentum moving forward. Just like a ball rolling down a hill, if you were to have some momentum on it and if it reaches a flat plane, it's still going to continue moving because of the momentum. The advantage of introducing something like momentum is very important for when we hit something called the local minimum. Our goal is to reach a global minimum of the loss function, but these local minimums are like smaller divots within the loss function that our model might think is the lowest point of the whole entire function. So here are some 2D and 3D examples of it. But when the model hits a local minimum, it's sort of a dead end, and we have to go back and adjust some of these parameters like the learning rate or adding in some momentum.
Sir, if you have a complaint, I suggest you submit it through our email system. I would be happy to refer you to our website.
You are done. Fired.
Now for this equation that has the momentum, all we're doing is adding in a beta term to the original stochastic gradient descent equation. This beta term is a decay factor that we've set before training. So we set it to 0.9, it takes in 90% of the old velocities of the previous layer and only 10% of the new gradients. The beta term takes in the momentum of the previous term and uses that to help push the model out of the local minimums. This momentum gives it the ability to continue moving forward even if it hits a local minimum. We're only going to be looking at these two optimizers today, but there are different optimizers depending on what you're trying to solve, what kind of data you're dealing with, and as you can expect, there's different trade-offs that's given with each one of these. So the main trade-off between stochastic gradient descent and the one with momentum is the one with momentum takes a little bit more compute power. So that's about it. I've pretty much explained just the general skeleton structure of a neural network where the model is being sent forward the data and then calculates a loss function, sends it back through, updates the weights. It continues that process over and over, trying to minimize the loss function eventually. In the next episode, I'm going to be looking at more architectural techniques that can help minimize our loss function.